Okay, so in this video, we want to find a way to differentiate inverse trigonometric functions. And as you will see, it's actually not that complicated. All we need is to understand what an inverse trig function gives us and simply use implicit differentiation. And you'll see this will be very similar to what we did with exponentials and logarithmic functions. So let's just start with understanding what a trig function gives us and what an inverse trig function gives us. So if you have a trig function, so a trigonometric function, well, what a trig function takes is an angle, right? Think of sine, cosine, tangent. You have a right triangle, and the trig function takes an angle as its argument. So a trig function takes an angle. And what does it give you? Well, if you think of sine of x, that would be the opposite over the hypotenuse. Cosine of x would be the adjacent over the hypotenuse. Tangent of x would be the opposite over the adjacent. So a trigonometric function takes an angle and returns a ratio of sides. The sides being of a right triangle. So of course the inverse trig function does the opposite, right? So if a trigonometric function takes an angle as its argument and returns a ratio of sides, the inverse function will do the opposite. It will take a ratio of sides and it will return an angle. So whenever you have the sine of something, that will be a ratio of sides, or any other trig function. So a trigonometric function of an angle gives you a ratio of sides, and an inverse trigonometric function will take a ratio of sides and give you an angle. And with this idea in mind, we can proceed. So we'll find first a derivative of arc sine of x. So we have the function y equals sine of x. And its inverse function, we usually denote it by y equals arc sine. So arc means the inverse function, so arc sine of x. And of course, the relationship between a function and its inverse function is that they cancel each other out via composition. So if I take sine of arc sine of x, well, arc sine is the inverse of sine, so sine will cancel arc sine, and we'll be left with the argument, simply x. And similarly, if you compose in the opposite order, if you take the arc sine of sine of x, well, arc sine is by definition the inverse of sine, so it will cancel the sine and the arc sine, and we once again are left with the argument x. And that is again the fundamental property of the inverse function. So now all we need to do is find the derivative of arc sine using implicit differentiation. So we're trying to differentiate the function y equals arc sine of x. So we are looking for, in this case, finding the derivative dy over dx. So what is the derivative of arc sine of x equal to? Well, if we leave it like this, if we leave y equals arc sine of x, this is actually not easy. We don't know. We have nothing so far that will help us differentiate arc sine of x. The idea is, if the arc sine wasn't there, maybe we could do something. Well, to cancel the arc sine, we have to compose with its inverse, the sine function. So now think of it this way. Y is equal to arc sine of x, so you can take the sine on both sides, right? So the sine of the left-hand side, which is y, will equal, and now you can make the substitution, because y is equal to arc sine of x, you can replace y by arc sine of x. But we know that sine is the inverse function of arc sine, so they cancel each other out, and we're left with quite simply the argument x. And then we have the relationship y equals arc sine of x in a different form, simply as sine of y equals x. Now both this equation and this one are equivalent, but if you notice now, the inverse trigonometric function is gone. And now we can differentiate using implicit differentiation. We know that y is a function of x, namely arc sine of x. So sine of y is a function of x. This is a function of x also. So if the functions are equal as functions of x, they must have the same derivative with respect to x. So the derivative of the left-hand side, which is sine of y, must equal the derivative of the right-hand side, which is x. And now let's differentiate using the rules of differentiation. So what do we have from the left-hand side? Well, here we have a composition. This is sine of y. By the chain rule, we'll differentiate the outside function, which is sine. The derivative of sine is cosine. Cosine of what? Of what's left over, which is y. But we're not done. There's a y left over. By the chain rule, we multiply cos of y by the derivative of what's left over, which is dy over dx. And that takes care of the derivative of the left-hand side. And this equals the derivative of x with respect to x. Well, that's just equal to 1. And now we can isolate for dy over dx, the derivative of arc sine of x, by dividing across by cos of y. So dy over dx is equal to simply 1 over cos of y. So we had the derivative of arc sine of x, right? Y was arc sine of x, and the derivative is 1 over cos of y. The only question now that's left for us is to ask, can we replace this by a function of x, right? Initially we had explicitly y as a function of x. Y was arc sine of x. So if we replace, we'll have cos of arc sine of x, and the question is, can we perhaps simplify this? Well, let's go back to what we said initially. An inverse trigonometric function takes a ratio of sides and gives you an angle. So an inverse trig function of anything is an angle. So here this is arc sine of y, arc sine of x, sorry. So this is an angle. An inverse trig function gives you an angle. So here arc sine of x is an angle, therefore y is an angle. Given any angle, we can always construct a right triangle. And now let's construct a right triangle whose angle is y, and let's see what we get. So we have our right triangle, and the angle that we choose is y. Another question is, well, what are the sides of this triangle equal to? Well, if we just go back, since y is arc sine of x, taking sine on both sides, it gives us that sine of y is equal to x, right? So sine of y is equal to x. And here I'll be a little silly. I'll say x is equal to x over 1. And if you remember, by definition, sine of an angle, if you think of your SOHCAHTOA, is the opposite side over the hypotenuse. So if you think of it, now we can construct parts of this triangle. Sine of the angle will be the opposite side over the hypotenuse. And if you think of it, well, the opposite side you can take to be simply x. And the hypotenuse you can take simply to be 1. And now with this we have two sides of our triangle. Well, we're missing the base, the third side, but we can complete this with Pythagoras' theorem, right? If we call this side, say, A, We know by Pythagoras' theorem that a squared, the base squared, plus the height squared is equal to the hypotenuse squared. And then we can solve for a. Subtract x squared from both sides, so a squared is equal to 1, 1 squared is 1, minus x squared. Solving for a is positive here, so a will be simply the square root of 1 minus x squared. And now we have a complete right triangle. The base is the root of 1 minus x squared. The height is x, and the hypotenuse is 1. And if we go back, well, the derivative of arc sine was just 1 over cos of y. But since we have a complete triangle, we can easily find cos of y. Right? So cosine of y. Again, recall your definition or your trick from SOHCAHTOA. Cosine is by definition the adjacent side, which is the root of 1 minus x squared. Cosine is adjacent over the hypotenuse, which is 1. So anything over 1 is just that same thing. So what we have is that cos of y is the square root of 1 minus x squared. And now we can substitute in here and write our final answer. Y was arc sine of x. So what we have here is the derivative of arc sine of x. Let's write that down here. So the derivative with respect to x of arc sine of x, the inverse function of sine, is equal to 1 over, right, if you just look back up, the derivative of arc sine was 1 over cosine of y, but we've just found that cosine of y is root of 1 minus x squared. So the derivative of arc sine of x is 1 over cos of y, which is, as a function of x, the square root of 1 minus x squared. And there you have it. The derivative of arc sine of x as a function of x is equal to 1 over the square root of 1 minus x squared. If you use the same argument, and I will let you do this on your own, you will find the derivative of arc cosine, the inverse trigonometric function of cosine, is actually really similar. It happens to be the negative of the derivative of arc sine. It's just negative 1 over the root of 1 minus x squared. And so you should, on your own, derive this formula in the same way that we've derived the formula for the derivative of arc sine of x. Well, there are 4 other inverse trigonometric functions. There is the arc tangent, the arc cotangent, the arc secant, and the arc cosecant. We'll do one more example for the derivative of arc tangent of x, and then I will give you the other answers for the other 3 inverse trigonometric functions, and on your own you should derive each one using the similar idea. So as our last example for this video, we'll find the derivative of arctan of x. Now that we've gone through one example, this one will be much faster. So we have y is the inverse function, so arc tangent of x. And we want, as before, this is an a, sorry, arc tangent of x. And as before, we want the derivative of arc tangent, so we want dy over dx. Well, again, we're not sure how to handle arctangent. To get rid of arctangent, compose with the inverse function, which is tangent. So take tangent on both sides. So tangent of y will be equal to tangent, and now we replace y by arctangent of x. They're equal. But again, tangent is the inverse of arctangent, so if you compose the two, they cancel each other out, and we're left with quite simply x. So what we have is now that tangent of y is equal to x. And this equation is equivalent to this one, but the great thing now is that the trigonometric function is gone from this equation, so we can once again differentiate using implicit differentiation. Because we know y is a function of x. This is a function of x which is equal to another function of x, therefore they have the same derivative. So if we differentiate the left-hand side with respect to x, and that is tangent of y, this will be the same as the derivative of the right-hand side, which is x. So let's differentiate. Once again, being careful by applying the chain rule. This is tangent of y. We have a composition. The derivative of tangent is, if you recall, secant squared of what? Of what's left over, which is y. But there is still a y that's left over. So we have to use here the chain rule and multiply what we have so far by the derivative of what's left over, and that is, of course, dy over dx. That takes care of the derivative of the left-hand side equals the derivative of the right-hand side, which is simply 1. So we can now solve for dy over dx. dy over dx is equal to, well, we just divide through by secant squared of y. So we'll have that dy over dx is 1 over secant squared of y. But if you think of it, we can do here a little simpler. Because, by definition, secant is 1 over cosine. So what we have here is 1 over cos squared of y. If you flip a fraction twice, you get its denominator. So we just get here cos squared of y. So now we have the derivative of y with respect to x. We have the derivative of arctangent of x, but once again, not as a function of x, but as a function of y. So we'll use the same trick building a right triangle to convert the answer here back to a function of x. Let's just rewrite what we have so far. The derivative of y with respect to x is cos squared of y. Well, look at your relation here. Tangent of y is equal to x. And remember, to build a right triangle, we need an angle. Well, if you remember, inverse trigonometric functions are angles. So this is an angle, and so y here is an angle. So we can build with y a right triangle. And now you say, well, how do we complete this triangle? Well, let's go back. Tangent of y was equal to x. So tangent of y is equal to x. But if you remember, tangent was SOHCAHTOA, the opposite side. Over the adjacent. So we would like this to be a fraction. The easiest way is to write x as x over 1. And now we can see that tangent of y being x over 1 will be the opposite over the adjacent. Therefore, the opposite side will be x. So tangent of y opposite, x, over adjacent, which is 1. So we now have the base of our triangle is 1. The height is x. Now we want the hypotenuse, which we can call c. But once again, we can now use Pythagoras' theorem, right? The base squared plus the height squared of a right triangle will equal the hypotenuse squared. We want to solve for c. Well, take the square root on both sides and you have it, right? So c will be the square root of this, but 1 squared is just 1, so we have the root of x squared plus 1. So there you have it. The hypotenuse of our triangle is the square root of x squared plus 1. And now we're good to go. We have a complete right triangle. So we can now find the derivative of arctangent as a function of x. It was cos of y all squared. But if you remember, cosine is the adjacent over the hypotenuse. So it's 1 over the root of x squared plus 1. Well, if you square this out, if you square 1, you get 1. And if you square a square root, the square root goes away, and you're left with x squared plus 1. So there we have it. Y, if you remember, was arctan of x. And so the derivative of arctan of x is surprisingly simple. It's just 1 over x squared plus 1. So there you have it. Now on your own, using again a similar argument, show that the derivative of the inverse function of cotangent, therefore arc cotan of x, will be again, surprisingly, just the negative of this one. So negative 1 over x squared plus 1. And that's how you differentiate arctan and arccotan of x. And finally, there are just two inverse trig functions that are left, and that is the arcsecant and the arccosecant functions. Well, let's just write their derivatives here, and once again, you should check that the result is true on your own, using a similar argument. So the derivative, this is what you will find, of arcsecant of x happens to be, and this one's a bit more complicated, it's 1 over x times the root of x squared minus 1. And again, interestingly enough, the derivative of arccosecant, the inverse trig function of cosecant, so arc csc, arccosecant of x, happens to be once again the negative of the derivative for arcsecant. So it's negative 1 over x times the root of x squared minus 1. And that's it. Now with this, you have the derivative for the 6 fundamental inverse trigonometric functions. And in theory, now you can differentiate any function involving inverse trigonometric functions. In our next video, we'll use these 6 formulas, the derivative for arcsine, arccos, arctan, arccotan, arcsecant, arccosecant, and we'll look at examples with these new rules of differentiation, these new formulas of differentiation. But make sure that on your own, you derive this, and this formula, and that will again lead you to a better understanding of inverse trigonometric functions and implicit differentiation.